Hello, everybody. This is Professor Ma, and this is the sections on power series. A power series is basically an infinite degree polynomial. And where do they come from? Well, they actually come from trying to answer the questions that suppose up two functions at x equal to a, and we got f of a is equal to some function g of a. On top of that, f prime of a is equal to g prime of a, and f double prime of a is equal to g double prime of a. You got my guess. Suppose everything's the same, same value, same derivative, same second derivative. What can you say about f of x and g of x? I don't know. Around x equal to a. Okay. So this is the question we're going to try to answer, and the motivation came from for the PowerPoint. So a PowerPoint is infinite polynomials written out in such a manner. And notice, doesn't matter what series power series I have, I can always plug in 0, and I will always get that first number. In other words, there's at least one number, 0, I can always plug in and I get a result. Then the question about power series is the following. What number may I plug in so that the series will converge, diverge, or what kind of convergence is if the power series turns out to be plus and minus, then the convergence is absolute or it's convergent conditional. Also, for example, here is a power series, and this is basically the pattern for geometric series. If I plug in a number for x, I get a geometric series. So I know what the convergence looks like. In this case, if I plug in any number between 1 and -1, okay, converges. Any number bigger than or equal to 1 minus 1, the absolute value, it diverges. So I have a pictures. So this is the pictures for the convergence or divergence of the given power series. Okay. And now what happens if I make the series, the series a little smaller instead of just x squared, x cubed? What happens if I divide it by 2, divided by 3, divided by 4? And then you can kind of see, well, this kind of comes in with the harmonic series. In this case, notice first, I can conclude for any number between 1 and -1 will converge. Oh, I mean, because I can use the ceiling converging theorems, okay? Let me remind you what this is. The ceiling converging theorem basically says if I find something bigger, a bigger one, okay, here's a bigger than mine, right? And this bigger one converges, okay? Then it acts as a ceiling, then this will imply these must converge because the ceiling is on top of what I have. So what I have must be smaller, so it must converge. So this P of x, the power series over here converge for every number x you plug in between 1 and -1. In particular, at 1, okay, in particular, if I plug in 1, then I get a harmonic series. It diverges. But if I plug in -1, I get the alternating series. Then this one, remember from the last sections, this one converges because this is a decreasing sequence in the absolute value is a decreasing sequence, and I'm taking alternating plus minus, plus minus, plus minus. Okay, and so this will converge to a number. This sum and difference will funnel back and forth to a limit, but its absolute value is a harmonic series diverges. Okay, so so this is the picture for the convergence or divergence of this power series, actually nth power divided by n. Okay, it almost like last one, it diverges on the red part and converge absolutely in the black portions, and at -1, it converges conditionally. This one's color coded. You can use any other symbol. You can use a square there, just indicating something different. So this is just for the point of PowerPoint, so I made it colorized. Okay, so here's the theorems about power series. And it basically says the 3 types of domain for power series. Okay, it converges at exactly 1 point. Okay, it's converges absolutely inside an open interval and diverges outside. And at a boundary points, like the last case we have for the harmonic series versus the alternating harmonic series, 2 ends. On the boundary points, you have to decide individually. So these we don't know. You have to investigate the series by plugging the R and minus R to see individually what happened at the boundary. Then the third case is converges everywhere. Oh, by the way, how big R is that's called a radius convergence, because you can kind of view that as a circle from 0 to R. Okay, then, and then the other case possibly is that it converges everywhere. It doesn't matter what number you put in, it converges absolutely. Okay. And so depends on then the coefficient, the pattern of the coefficients, the AN, then it determines the type of algebra we're going to apply. Then we can figure out what the radius convergence is. So like for instance, here, n factorial. And what type of test is good for testing convergence? Well, this one we use ratio test. Why? The reason we use ratio test is because n factorial and m plus 1 factorial cancels. So this is the only, basically the only algebra that we have for factorial. That is m fact plus 1 divided, and everything behind it is m factorial cancels out. So the only thing left is m plus 1. So this type of algebra gives us the using the reason for to use ratio test. So what's a ratio test? Well, so we take the ratios, it's supposed to be less than 1, it will converge. Okay, we're going to wind up with a formula with x in it. We want that to be absolute value with x in it. We want that to be less than 1, then we can see what x is. So anyway, so I take the coefficient, ratio of the coefficients. By the way, the coefficient for m plus 1 is m plus 1 factorial. Okay, x m plus 1 over m plus 1 factorial times reciprocal of the terms an, which is m factorial over xn. Okay. And cancel everything, I wind up with x over n plus 1. Now, what's the implications of this? Now, remember, we want to investigate the limit as n goes to infinity. Okay? And we want this limit to be less than 1. You say, what's the x doing there? Well, x is a fixed number. So, in other words, choose an x, fix an x. Okay, let n go to infinity. Well, the limit is 0. Okay, for any real number you choose x, you use this test, and you find out the limit is 0, which is less than 1. So in every number you plug in, you do this ratio test. So in other words, you're not doing ratio test for just one number. You're doing ratio test for every number x. And then the result is the same, because for every number x you fixed, you let m become bigger and bigger, it goes to 0. It's less than 1. So for that particular x, therefore it converges absolutely. Okay, and that's it. So in other words, for this particular power series, it converges absolutely for all numbers. So again, the algebra we choose is a ratio test because the coefficient involves factorial, which will cancel. Okay. And word about what happens if I do something like putting an n+2, then the idea is you can first you use a ratio comparison test to drop that pass, then you pull these tricks, right, arguing this way. So there'll be two steps. Okay, the first step is clean up the coefficient, throw away the parts that's not important, and then that surrogate copy Bn, you use that to decide the convergence and divergence. Okay, so that's the steps for calculating the convergence, divergence, the radius of it. So this one converges for every number. Now, this one, well, that obviously in this case, it's easier to use a root test because I can take the nth root of these numbers easily. And the root test says if the nth root of the nth term is less than 1, as the limit goes to infinity, converges. Okay. And then it's very easy to calculate the nth root of the an's terms. It's just x over 2. Okay. I want these to be less than 1. Okay. Now again, we're going to plug in x. And now the question is for one number x I plug in, it will be less than 1. Notice this expression is different from the last one. This one has no n in it. Okay, the n is already gone. So the only number you can plug in to be less than 1 here is x is between 2 and -2. So the radius convergence is 2. And now, we have to decide, remember, so we now have decided that it converges absolutely between 2 and -2. Okay, it diverges outside, it converges inside, converges, okay. And then the question is what happens at 2 and -2? This is where at the boundary of the radius convergence, we're going to plug in each number into the power series, where I get a series of numbers, then decide individually converge or diverge, or what type of converging it is. If I put in 2, it diverges. Putting -2, diverges. Okay, so therefore, here's a pictures of the convergence, radius converging for this series. It's okay. Diverges, in the middle, converges absolutely. Okay, from -2 to 2. Okay, -2 to 2. Let me put it this way. Now, we can have power series, and the power series we say is this power series. Let me write it out. Sum a and x to the nth power. We say this actually is came from a form x minus 0 to the nth power. So the action is concentrated at 0. Now, if I want to look at a different type of power series where the thing's not centered or concentrated at 0, but at some number a, okay, to the nth power. So we can write this type of power series where it centers at a, some arbitrary number a, whatever a we want to be. You will see later on how we're going to use these two types of power series. Okay. So we call this power series center at x equal to a. Okay. Notice again, I mean, if I plug in number x equal to a, then I will get a number. If I plug in x equal to a, then all these disappear, and I will pick up the first number again, just like the power series center at 0. Okay. And then the picture for convergence or divergence equal convergence at a. Remember, I can plug in a, you get the numbers. And it's exactly the same as around 0, except now you are doing it at around the point x equal to a. we shift the entire action to somewhere else. So discuss convergence, divergence of these. Okay. Now you will see we're going to do exactly the same type of testings as before, except now you're going to wind up with an inequality about x minus 3, not about x. Okay. So we're going to use a ratio test because things will cancel nicely. Okay. So the m plus first terms is with x, of course, and at m plus 1. And then nth term is this turned upside down. And then we look at the algebra. Okay, what algebra? Limits. Okay, we're going to let n go to infinity. And then it's very easy to see this. You have to verify on tests. Okay. Usually L'Hopital's rule. Okay, at least I need to say something. Why does go? Why do that limits each one goes to 1? So you want out x minus 3. Okay. And the rate then these will converge if this number is less than 1. So that means x is between 2 and 4. So for interval 2 and 4, that's the interval convergence. Okay. And sentence at 3, you will see the picture later on. And at 4 and 2, you plug it in individually to find out whether the series converge or diverge. So if I plug in 4, I get this series, and this series is bigger than harmonic series. Log n is bigger than 1. Okay, so these will diverge. Okay, but if I put in minus 1, and then this is say decreasing sequence with alternating sum. So this one converge, and so it converges conditionally. So this is the pictures for the convergence of the series we have, which was what? Which was some ln of n over n x minus 3. Okay, 1 to infinity. Can be 1 because that's 1. No, can be 1. Okay. And in particular, if I plug in number bigger than 4, it diverges. But if I pick number between 2 and 4, it converges. And at boundary point 4 and 2, the behaviors diverge and converge conditionally. Okay, so that's it. Mm-hmm.